Today we're going to cover the sequence of operation for an 80% gas furnace. This is very similar to several other models, but I'm going to focus specifically on this one. I'm going to roll through it pretty fast at first, then we'll go through and break down all the steps. So to get started, the thermostat calls for heat, connecting R and W, sending 24 volts to the IFC. The IFC does a safety check of all the safety components. The IFC then energizes the inducer draft motor, pulling a vacuum through the heat exchanger, which we call a pre-purge, about 30 seconds. It pulls a vacuum to the negative pressure switch, which closes, sends 24 volts back to the IFC. The IFC then energizes the hot surface igniter to start getting hot. The IFC then energizes the combination gas valve, allowing gas to flow through the manifold, to the spud, through the orifice, where it mixes with primary air inside the burners, across the hot surface igniter, where it ignites to a flame burning inside the heat exchanger. The flame sensor has a few seconds to prove a flame through a process called flame rectification. Once the flame is proven, the IFC shuts off the hot surface igniter and keeps the combination gas valve on. The IFC is going to let the heat exchanger heat up. Then the IFC is going to bring on the blower motor, circulating the heat into the house. The whole time, the IFC is going to monitor all the safety components of the system. Once the house heats up, the thermostat satisfies, breaking R and W, killing the signal for heat to the IFC. The IFC immediately shuts off the combination gas valve, which immediately kills the flames. The inducer fan motor stays running. The IFC lets it run for approximately 30 seconds and then shuts it off. This is called post-purge. The IFC lets the blower run to cool off the heat exchanger and get that efficiency of the heat back into the house. Then the IFC shuts off the blower motor. That's a sequence very quickly. But if we break it down, there's a lot of steps, a lot of very important steps in that. One step is the thermostat calling for heat. The word calling for heat is a vocabulary word that we use in the trade. It calls for heat. The thermostat's nothing more than a switch. That switch connects the R and the W terminal. You can use any color wire you want, but the terminals it's connecting is R and W. On the control board, we also have an R and W terminal. So on the control board, what we're going to do is we're just going to jumper R to W to do exactly what the thermostat does. The IFC energized 120 volts to our inducer fan motor, which ran and pulls a vacuum. It pulls a vacuum to the pressure switch. This is also called a snitch if you want to. It closes. It makes sure that this guy is running right here. It tells the control board that that's running. When this switch closes, the IFC knows it's closing. Now it's getting the hot surface igniter hot. We're going to zoom in so you can see the hot surface igniter getting hot. Then the IFC is going to energize the combination gas valve, allowing gas to flow through the manifold, to the spud, through the orifice, mixing with primary air inside the burners, igniting into a flame burning inside that heat exchanger. That flame sensor has a few seconds to prove a flame through a process called flame rectification. Once the flame's proven, the IFC shuts off the hot surface igniter because we don't need it anymore. The IFC keeps the combination gas valve open so the gas continues to flow. The IFC is going to let those flames heat up that heat exchanger. Then it energizes the blower motor and starts moving air into the house. Now, a few things I want to point out is I have this door, we're going to zoom back out, I have this door off right now. Now, that's not good. Just for test purposes, we can do this, but you never want to have this door off because the blower is actually pulling air from the burner compartment. The combustion air of the furnace needs to always be separate from the airflow of the house. So now we're going to do a breakdown. We're going to go through the end cycle. The thermostat satisfies, breaking R and W. Notice how the flames immediately shut off because the IFC immediately shut off the combination gas valve, immediately stopping the flames. It keeps the inducer fan motor running for a little bit, then it cycles it off. The IFC cuts it off. The IFC is going to keep this blower on, circulating heat into the house, that last little bit of heat, and to cool that heat exchanger off. We don't want that heat exchanger to crack. We paid money to buy gas for that heat. We want to make sure we're getting that heat into the house. Some of these control boards have an adjustable off delay. This particular one does. It has actual jump terminals. Some of them have dip switches that we use, but you can adjust how long that off delay happens. For example, you have an elderly customer, as this thing is cooling off the heat exchanger, they feel what they call a cool draft in the house. They don't like that. You can actually slow the blower delay down to where it only runs for a shorter period of time. So that way they don't feel that cool draft. For efficiency, you want the blower to run for as long as possible, so you get every little bit of that heat into the house. So it's always a balance. Most control boards allow you to adjust that off delay, but I have yet to see a control board anytime recently that had you the ability to adjust the on delay. So when the flames hit and it starts heating up that heat exchanger, the engineers have designed exactly how much time it needs for their furnace before they send that blower on. And that's important because when these flames heat up that heat exchanger, it needs to get to a certain temperature at a certain speed so that it has complete combustion or nearest complete combustion as possible. As this heat exchanger is too cool and those flames heat up, you're going to have an issue with smog, carbon monoxide, soot building up inside the heat exchanger. So they've designed that on delay, how long it takes between the flames and that blower coming on, is a set. So this thing's about to cycle off. Hopefully you'll be able to hear me a little bit better after that. And we're going to go through that sequence of operation again, and now we're going to add the diagnostic aspect to it. Perfect timing. So when we say the thermostat calls and the thermostat satisfies, it's vocabulary words that we use in the field. Calling for heat means it's connected to wires, and satisfies means it's disconnected to wires. Remember, this is just a switch. And the heating side, we're only concerned about the R and the W terminal. So when it has a call for heat, it connects to R and W. When it satisfies, it breaks the R and W. So when we say the sequence of operation starts with the thermostat, that's where we start. Is the thermostat calling for heat? Or is it satisfied? Now remember, it's not just a thermostat. These 24 volts from the W wire have to get all the way back to the control board. This is where a meter comes in handy. I can check between R and W and see I should have 0 volts if it's calling. If I'm reading 24 volts, then that means the thermostat's either not calling or the wire's broken somewhere between there. So we want to make sure the thermostat's calling for heat, that we're getting 24 volts all the way back to the IFC. If you're in an attic on a 2-story house or on the roof of a commercial building, you may not want to walk all the way back to the thermostat to turn it on. You can simply use a jumper wire and connect R to W and have that call for heat. Now this IFC, there's many, many types of IFCs out there, hundreds of different styles, but they all do the same basic function. The engineers have designed what they want it to do. So the IFC is going to use one of these relays right here, and it's going to energize this inducer draft motor. Now what I want to point out to you is this inducer fan motor is pulling a draft through the heat exchanger. It's pulling the flames, the fuel mixture, through the heat exchanger, and it helps start or induce that draft through the flue pipe up here. But what's important is this flue pipe is a negative pressure flue pipe. It's still relying on natural draft to carry it out. It's not pressurized. A lot of people think because we have this fan motor, this is a pressurized pipe. And the truth is, this fan motor is too small to pressurize this pipe. It still relies on natural convection for it to heat up. We have double wall vent pipe right here. That inside pipe has the heat up so it can naturally draft out. A lot of people have tried to use different types of piping or different types of vents on the roof, and they think that as long as it's pushing it out, they don't have anything to worry about. And that's false. This is a natural draft. The only ones that are positive pressure, different type of heat exchanger, usually the ones with PVC, that's the ones that's forcing it out. Now we're going to talk about this inducer fan motor. It's just like a miniature blower motor. So you got these little fins right here, and these usually come in a complete kit. So when this gets 120 volts, on this IFC, it's got these relays that energize 120 volts to this motor. This motor starts running, and as this motor is running, it starts pulling that draft and forcing it through that vent pipe. These fins can easily get corroded, burned up, especially if you have a leaking flue pipe or incomplete combustion. These things will burn completely up. So it's very important that those are working. And as it pulls a draft through the heat exchanger, it's also pulling a draft through this little tube to the pressure switch. Now if we look inside of this motor, I've taken the wheel off of this one, and you can see this little hole right here. That little hole is where it's pulling the draft through here. The fan blade's been removed and it's pulling a draft. It's negative pressure. On this particular one, it's corroded up. So this has had moisture coming into it. That hole right there can corrode up. So remember we say it's going to pull a draft, pull to the pressure switch? Well, if this wheel is corroded up, if the wheel's not working right, if that hole is corroded up, it won't be able to pull a vacuum to the pressure switch. Also, if we look at that same thing, this hose right here can become cracked. I've seen the plastic break, so as it's pulling a vacuum, it's not pulling a vacuum to this pressure switch. There's many different styles of pressure switch available, but they all do the same thing. They simply close when there's a vacuum being pulled. Now, on that, you can't just replace any one of these, even though they do the same job. they have different pressures that they open and close with. This particular one here breaks at 0.27 inches of water column, and it makes at 0.42 inches of water column. So they have different settings when they open and they close by design. So there's a way to test this. You can actually put a T in this hose, or you can keep a spare set with you with a T on it, and you can check the water column on that while the system is running. It's going to pull a vacuum. You can see what the vacuum is. Field piece makes a really nice little meter that you can actually disconnect the hose entirely, hook it up to the instrument, hook your wires up to the pressure switch, and it tests that switch for you individually. Another thing that we can do to check to see if that switch is closing is we can pull these wires back just a little bit. We can use our meter and we can check for voltage. If we're getting 0 volts across there and this motor's running, we're getting 0 volts across there, the switch is closed. If this motor's running and we're getting 24 volts across there, that switch is open. So a lot's happening just between this motor happening and this switch closing. So you don't just say, hey, this switch is not closing, it's bad. Let's make sure, is it getting the vacuum all the way to there? This is what you need to be thinking about. This is what the control board sees. It energizes this. It can't tell if it's working. This is the snitch saying, hey, this guy's doing his job. We're okay, keep going. So after we know, the control board knows that this is working by the pressure switch, it then energizes the hot surface igniter. There's many styles of hot surface igniters. I love these newer styles because they're built a lot better. The old ones, if you tried touching it like that, you're done. They would crack. You could look at them wrong and they would break. These new ones, the silicon nitrides, are really nice. They're heavy duty. They last a whole lot longer, but this is one of your big fail points. This is probably your biggest replaced part. They last about 5 years or so, but to see if this is working, if it's getting bright red hot, you know it's probably working. If it's not, well, that's the sequence of operation. Make sure this switch is closing, that switch is closing, this isn't lighting up, let's check this switch. Another way to check it is you can unplug the plug to the hot surface igniter. You can actually check for voltage coming to the igniter in the proper sequence. You got to remember that it's not going to have voltage all the time. It's got to go through the proper sequence. So if I'm getting voltage here and I plug this back in and the pressure switch is not getting hot, then we know there's an issue. We used to teach to ohm out these pressure switches. We used to teach to ohm out these hot surface igniters. The problem is there's so many different brands out there now and so many different manufacturers that have a variety of different ohm readings that they want on these. It's really not an accurate way anymore. You'd have to find out from every single manufacturer what the resistance should be and what the allowable is to know. I still old school. I like to ohm these out to see what my readings are, but it's really not as necessary. Remember, if you're going to ohm it out, you need to disconnect the component entirely. Now it's isolated. Now I can use ohms and check this. So now that we've got this heating up, it's not going to heat up instantly. It's going to take a little bit of time for it to get to its optimum temperature. That's why there's a delay. Once it energizes this to come on, the IFC then energizes 24 volts to our combination gas valve. Now it's real important that I use the word combination gas valve because it's a combination of 2 points, a pressure regulator and also a solenoid valve. This one has 2 valves, most of them do. It's called a redundant valve. They're in series to make sure that when it shuts off, it really shuts it off. But we have these 2 wires that come in here. When 24 volts go, it opens this valve and allows gas to flow. The reason I want you to call it a combination gas valve is because it's also a pressure regulator. So you got to make sure you have gas pressure coming in and then it's reducing it to the correct amount of pressure coming out. I've had before technicians that go to customers' houses diagnose that they got a bad gas valve, and the real reason is they didn't pay the customer didn't pay the gas bill, or something happened with the gas bill. Now they're trying to sell them a new combination gas valve and they don't have any gas to the house. So you got to think, do I have the proper gas pressure coming in and the proper gas pressure coming out? We'll do gas pressure in a separate video and how to in a separate video, but this is a combination gas valve. So you got to diagnose it as 2 points. So you want to see, am I getting 24 volts to this gas valve? Hook your meter up with your wires, and you have to wait for the proper sequence of operation. So after we get our hot surface igniter lined up, we only have a few seconds that we're going to get 24 volts to this gas valve for it to open. Once we see that this valve's opening, we can look at the pressure. Most all of these gas valves have an output pressure port that we can check. All different types of manufacturers, all different ways of doing that. RTF filmed on that manual to see if you're doing it the correct way, but it puts output pressure. It's called the manifold. So leaving the combination gas valve, we have the manifold. It takes the gas from this one valve and separates it to multiple points. So this is the manifold. It's also called manifold pressure. You're going to need to read the manufacturer's instructions, but typically, this is not set in stone, but typically you have 3.5 inches of water column for natural gas and 11 inches of water column for propane. That's in your manifold. Don't go by those numbers. Check with your manufacturer and make sure that's what they want for that altitude. So gas flows through the manifolds, then it's going to go to this little component right here. And what I've done is I've taken one of these off, and this is called a spud. I have no clue why they call it a spud, but it's called a spud. And on these spuds screw into the manifold. There's a number stamped on here. This particular one's 44. That number is the size of the hole. Another word for hole is orifice. So gas flows through the combination gas valve into the manifold, to the spud, and through the orifice. Now it's shooting gas out of this orifice. Now that number, the size of that number, depends on the manufacturer and the altitude. Different altitudes sometimes require different numbers for gas regulation, and there's certainly a different number between propane and natural gas. We'll get into that later, but a lot of units have been ruined because they weren't converted from natural gas to propane correctly. So gas flows through the manifold, to the spud, through the orifice, the hole in the very, very center. Then as it gets interesting is it goes into the burners. Now the type of burners that we're going to be using is called an in-shot burner. So this is a burner. It's called an in-shot burner. It's shooting the gas into our heat exchanger. A lot of people call these jets. That's perfectly fine. It is an in-shot burner. So the spud and the burner hook together. Now if you notice, it's shooting gas to the very center of this hole. As it shoots gas to the center of the hole, it's actually pulling air in around it. This effect right here is it's shooting the gas in, it's pulling air. This is primary air, not just air. We have two kinds of air: secondary air burning around it and primary air. That primary air needs to mix with the gas inside this burner. Burners do two jobs. They mix the air and the fuel, and they direct the flame. So here we're mixing the air and the fuel, and then we're directing the flame coming out. So this is an in-shot burner, and it's important to see that there's little bitty lines on both sides of these. There's another one that lines up beside this one. So the main flame's coming out into the heat exchanger, but there's also this side tube right here that lights the next burner. It's important to make sure that these don't have rust or anything like that. They can start to rust up. That can be an issue. You can pull them out and clean them, but you need to be thinking, if there's rust on this, where's the moisture coming from? Is it leaking water? There's some other issue you need to get fixed. I've seen these units that were 20 years old that never had a bit of rust on them. So if there's they're rusting up, you need to be thinking, where is that coming from, and where's that rust, what else is that rust causing? So once we mix the air and the fuel inside the jets or the burners, in-shot burners, it's going to go across this hot surface igniter. So the flame shoots across this hot surface igniter. This is bright red hot. It ignites it into a flame. Now that flame can't just burn anywhere. It needs to burn inside that heat exchanger. And ideally that heat exchanger needs to be in really good condition because it needs to keep the flames and the burnt fumes separate from the air in the house. Think about an exhaust pipe on a car. You get an exhaust pipe leaking, it can leak carbon monoxide into the cab. So these tubes are very similar to that. We're burning the flames inside the tubes, and the air from the house is outside the tubes. It keeps them separate, but it exchanges the heat from the flames and the gases to the air inside the house. So it keeps them completely separate. We want to control that. Now, we only have a few seconds to prove a flame with a process called flame rectification. So here I've taken the burners out, and we have over here a single rod. And this single rod will only have one wire to it. Almost everything has at least two wires to it to open and close, measuring things. But the flame sensor only has one wire going to it and one rod. Notice it's igniting the flame on one side. It carries across all these crossover valves to my flame sensor on the opposite side. And notice it said flame sensor, not a heat sensor. It uses a process called flame rectification. I'm going to do a separate video just on flame rectification, but it actually takes the AC current from this rod, and the flame conducts electricity to a very small, a micro DC amps, but it's microamps is what it's measuring. So it converts it from an AC to a DC current, a pulsating DC current that this control board is reading. So it only has a few seconds. It gives it a few seconds to prove a flame through that process. This is one of your most service calls for heating. Is this flame sensor gets dirty, it has to be cleaned. There's a special way of doing that. We'll save that for another video as well. So once that we've proven a flame through flame rectification, that's where this blower is going to let that heat exchanger heat up. Then it's going to energize the blower, and all these relays on here energize all these different things. We're sending 120 volts to this blower. Now we're moving the air in through the house. So the house heats up. The thermostat's going to want to satisfy breaking R&W. When it breaks R&W, it immediately shuts off this combination gas valve, immediately killing those flames. We don't need heat. We're going to shut those flames off right away. But if you notice, this motor kept running, and what it wants to do is post-purge, post being after, clean out the heat exchanger. Any of those fumes that are in there, it wants to help pull those fumes out of the heat exchanger, get some of the clean air in there, so that way we're ready for that next process for heat. Once it's done that, few seconds, it shuts this off. It keeps that blower running to cool off the heat exchanger, and that's what some manufacturers allow us to adjust, that off cycle. Now the system's off, ready for the next cycle for heat. One of the biggest things you need to know about gas furnaces is that sequence of operation. If you know how the system operates, then you can diagnose it, or diagnose most of it anyways, and also helps you understand what's happening with that system. And your customers are going to expect you to know what's going on with the system. Sequence of operation also helps you diagnose it. So it's two very important sections. There is much, much, much more that goes into this gas furnace. All these safety components that we need to be checking, and that the control board checks, we're going to talk about those. We're going to talk about combustion analysis. We're going to talk about checking for carbon monoxide. I have my personal CO monitor with me, with the carbon monoxide monitor, and also my gas leak detector to see if there's any gas leaking. We're going to go and break down all these components, but that is our basic and short, fairly short sequence of operation of an 80% gas furnace with a hot surface igniter.